time, so let's get started. People coming in, grab a seat. Thank you all for coming. My name is Gabel. I work for an Israeli company called Wix, and last year at GeeCON, I gave a different talk called How Shit Works Storage, which was kind of the first in the series. So the idea behind this, other than my own personal gratification at being able to use swear words in a title, is basically to take like everyday kind of things that are part of part of the systems we build, that are underlying the code that we actually write, and peel off a few layers of abstraction and try and see if we can understand better how they work and what ramifications these things would have on the way we write our code. This year we're going to be focusing on the CPU. And in order to do that, the first thing I need to do is to give a bit of disclosure. So I'm not an expert on CPU design, hardware design. I'm not an expert on anything, really. What I have been doing is doing a lot of software development for quite a few years, and I have a very fundamental interest in the underpinnings of the technology that we actually use every day. So with that, be aware that some of the things I say are likely to be oversimplified. They might be slightly inaccurate. I could be wrong. So if you catch me at being wrong or you have something to add, please raise your hand or shout out. This is, it can be interactive or not, up to you guys. We're all here to have fun. One other thing is this topic, like the design, the architecture of CPUs, is just crazy complex. It's a huge topic. There's been 50 or 60 years of progression in the industry of hardware designers at Intel and AMD and other companies pushing the envelope. So we're only going to scratch the surface, right? There's only so much you can say about such a huge and complicated subject in about 40 minutes. But I want to give you some idea of how these things are built and what kind of effects the architecture of a CPU would have on your code. So to kind of set the stage, let's start with, this is a Java conference. I've given this talk at a different conference that was not about Java, and everyone was panicking about the fact that there's a Java code sample. This is not going to be a problem here, I hope. So let's get started with a bit of a riddle. We have this piece of code. We first do a bit of setup. We create a byte array. It's 32K of whatever size. We fill it in with random bytes. The next thing we're going to do is we're going to iterate over that array, and we're going to pick every positive element and just, add them to an accumulator, just sum them up. And a different variation of the same kind of really artificial but representative algorithm is if we do the exact same thing except we add a sort before the iteration loop. One of these two versions, the sorted and the unsorted version, and I'm just talking about the iteration. I'm not talking about the setup or anything. Just the inner loop, the iteration. In one of these versions, it's running significantly faster. So I want to pose 3 questions to you. First is, which of the 2 versions is faster? Anyone care to take a guess? Okay, so there's a unanimous shout of the sorted version is faster. Anyone care to take a guess by how much? 100 times I've heard. Any other guesses? 666, a very round number. Any other guesses? Okay, so we have 100 or 666 times faster. The third question is, can anyone, like those of you who have run into this particular issue before, please keep mum because that ruins the fun. But those of you who haven't actually seen this before, care to take a guess why? Anyone? Prediction. Branch prediction, that is one possibility. Any other takers? So CPU cache. Any other ideas? I couldn't hear that. The number representation? Not quite sure what you mean by that. But okay, well, CPU caching and branch prediction are kind of the 2 expected answers, and we're going to be focusing on them for most of this presentation. So that's quite all right. And I'll give you the answer in a full-blown explanation towards the end of the talk. But first of all, let's look at the results. So this is the results of a JMH benchmark. The code is on GitHub. The link will be at the end of the presentation if anyone's interested. And you can see that the baseline version takes about 115 microseconds per iteration of the loop, whereas the sorted version takes 13. So we have an order of magnitude difference in performance. And this is on exactly the same code, the same JITted assembly instructions. I even tested it on the same data set. The only difference is whether or not the byte array is sorted ahead of time. That is the only difference. So this gives us a conundrum. This gives us something to kind of look at and try to understand, what happened here? Why is it faster? What's the difference? The gist of this talk is that CPUs are really, really complex beasts, right? This is an electron microscope photograph of a CPU. This CPU is about 30 years old. It's an 8286. So just to give you some idea of the level of complexity, this is like an ancient CPU, right? Compared to what we're kind of used to today, this is prehistoric times. And there's still so much complexity here, it's hard to get a handle on. It is known that your high-level code in Java ends up getting compiled or JITted, in the case of Java, into assembly instructions. Now, you're not actually expected to read this, and we're not going to dive into assembly because that is not the point. If you're anxious to try and figure out this code, you're welcome to it. The end result will probably be this. So just don't bother unless it's like really in your domain of interest. What is slightly less known is that these assembly instructions, as they go through the pipeline and into the CPU, they're not actually executed atomically. It's not like the CPU takes in a move instruction and just executes it, right? You can think of low-level assembly instructions as kind of the API that the CPU represents to you as a software developer. But in actuality, it's a layer of abstraction because under the scenes, there is a lot of stuff that happens just to execute your instruction. So any instruction goes through 3 to 5 lifecycle phases, and this is largely true of any CPU architecture, not just x86. The instruction first has to be fetched from memory because, obviously it needs to be read off from somewhere, needs to be decoded, it needs to be executed, and then you have 2 kind of optional steps that depend on what the instruction actually does. It may do memory access. It may require actually reading stuff off of memory. So if you're storing, say, a word in memory, then you actually have to do that, or reading a word off of it. And then you have the write back phase. So any instruction that actually is effectful, that does a computation or stores something in memory or any of these things actually it modifies the state of the machine. Right, so you need to have some phase in which these changes are actually affected on main memory, the CPU register file, whatever the case. These are the steps every single instruction, and I mean assembly instruction in this case, goes through on your CPU. So to get a little bit better handle on what that means for us, we need to have a very kind of rudimentary overview of CPU architectures. This is an architecture diagram, once again, of an 8086. It's obviously very simplified because, as you saw before, the actual CPU is a lot more complex than this. And you don't really have to get anything out of this because we'll zoom in on each of these constituent parts in turn. So, what does a CPU do? We've covered kind of the basic phases of an instruction lifecycle. So the first thing the CPU needs to do is it needs to fetch the instruction, it needs to read in the program. For that, the CPU actually has to talk to main memory. As you know, main memory typically resides in these, back in the day it used to be SIM, now it's DIMM slots on your motherboard, right? It's external to the CPU, so there needs to be some unit in there that actually knows how to talk to main memory. For an old CPU like the 286, this is called a bus unit. The second thing the CPU does is, after having read in the instruction, it figures out what it does. This is called the instruction unit, or for other CPUs, the decode unit. Then it needs to actually do the computation. And there you have a number of units, the most famous of which is the ALU, or arithmetic logic unit, that actually does the thing that you told the CPU to do. It might be adding to numbers, subtracting to numbers, multiplying to numbers, whatever the instruction actually does needs to be executed somewhere. This is the execution unit's responsibility. Then you may need to talk to memory again in order to, say, read stuff off of memory. Once again, we have the bus unit, but we also have an address unit. Because as you know, certainly on modern CPUs, when you actually read stuff from memory, you don't really read stuff off of the physical address that you've specified. It goes through virtual memory and paging, and it gets mapped to stuff. And there's protected mode for those of you who have been around long enough to actually know what that means. So there's a whole unit in the CPU that's responsible for taking a logical address that your program actually references and translating it into a physical hardware address that it can then access on main memory. That is the address unit. Then you may need to perform I/O. So a lot of the times, what your code does is actually, certainly in the case of like device drivers and stuff, you might read things off of the network card. You might beep in case of, a PC beeper. You actually have to control the clock. You have to do a lot of these operations on top of hardware inside your computer, and you need some unit that allows you to do these things. This is another part of what the bus unit does. The gist of it is that there's immense complexity under the hood, right? Even an old CPU like a 286 just carries immense complexity that you fortunately don't really need to know because it's all abstracted away from you. But sometimes it is valuable to know it because it actually has ramifications on your code. One kind of last word on the construction or the architecture of CPUs. You basically have 3 categories of atomic execution units within your CPU. You have your LU, which is what most of us think of as the CPU. This is the part of the processor that actually deals with computation. It does branches, conditional checks, memory access, algebra, all of these kind of low-level things that our code actually performs generally are the responsibility of the LU. Traditionally speaking, you also have your floating point unit, which is a separate part of the processor charged with dealing with floating point numbers, not just integers. And then you have your memory management unit, which is the part of the CPU responsible for translating virtual addresses into physical addresses, dealing with memory mapping, paging, memory access control. This is the unit in your CPU that makes sure that if you read off of an invalid address, your process segfaults and it doesn't bring down your whole operating system. And these are kind of the 3 basic building blocks that we interact with as software developers, whether directly, for those of us actually building like device drivers and stuff, or through a stack of abstractions for most of us working on enterprise software in Java. Now comes the interesting part. So we have an instruction, and an instruction has its life cycle. Those 5 phases: fetch, decode, execute, memory access, and write back. How would we implement this, right? The funny thing about CPU architecture is that engineering is kind of the same regardless of what your discipline is. The details are very different, but the fundamentals are the same. So if you were to design a CPU, you might naively say, well, I have these lifecycle steps. I can do it sequentially, right? I read in an instruction, and I just go through all of these steps one by one for each instruction. Now, this is very, very easy to understand and also easy to implement, but it has an issue, and that issue is latency. If a step in the life cycle of a particular instruction takes a single CPU cycle, the throughput here is lousy, right? It takes 5 CPU cycles to deal with. The word that is commonly used is retire a single instruction, but you deal with them sequentially, so your throughput is basically 0.2 instructions per clock cycle, and that is bad. One almost trivial optimization that you can do is you can pipeline the thing, right? If you have separate units within your CPU responsible for each kind of step in the life cycle of an instruction, there's nothing to stop you from doing those in parallel. So you might, just do each one of these steps in parallel, and then ideally, if nothing else is stopping you, you still have the same latency because you still have to go through these 5 steps, but you can retire an instruction on every CPU cycle as long as you can keep feeding the pipeline and keeping all of the various units in your CPU busy. So that is like really the bare bone optimization. I think the first x86 CPU to actually do this was the Intel Pentium, but I might be wrong on that. It might have even been earlier. Pipelining actually adds a number of issues, and these issues basically revolve around concurrency. Because due to concurrency, a pipeline can stall. And what do I mean by that? If you have a branch instruction, so let's take a look at this. I wonder if, yep, the laser pointer works, cool. Let's take a look at this very uninteresting but representative if statement, right? What is kind of the underlying assembly that goes through the CPU? So the first thing you do is you need to memory load, right? You have your variable I somewhere in memory, you need to actually read off the value. So you set up this pipeline for dealing with the memory load instruction. The second thing you need to do is you need to actually perform the test, right? Your predicate in your condition in this if statement actually needs to be evaluated to determine which side of the branch to jump to. That was weird. Then you have your conditional jump, which is also an instruction. So kind of what happens next, right? The CPU doesn't know because the flow of the program depends on your execution path. It depends on the result of computing this predicate. The CPU doesn't know which way to turn. So if that happens, it can't feed anything into the pipeline ahead of time. It just doesn't know which instruction to read off of memory. So that causes a pipeline stall, right? The pipeline is not fed with data fast enough, and it just needs to sit there and wait for new information, new instructions to come in, and that slows everything down. That reduces your throughput. More importantly, this happens with dependent instructions. So if we have, once again, this very artificial code, let's assume that our compiler is very naive and it doesn't do anything smart. So you have, fortunately, most modern CPUs have an atomic increment a memory address instruction, so it's just 1. Then we need to load the new value from memory. We add 1 to it, and we store the result in the variable known as x. What does the execution look like here? Well, the first thing we do is we fetch the memory load instruction. Then we can execute it while fetching, the first thing we do is we fetch the increment memory. Then we can fetch the load from memory instruction while decoding the increment. Then we execute the increment while decoding the load from memory, and we can feed a new instruction to the pipeline. That would be adding 1 to x. So far, so good. We can do memory access, read off the original value of I as part of the first instruction, execute the load from memory, decode the add, and fetch the store. All of this happens in parallel. But the next step is a bit of a problem because you get to actually writing back the effects of your memory address increment, like the first instruction, the I++, while you get to the memory access for loading the new value of I. Right? These things have to happen in a deterministic order, or you get what in software you would call a race condition. Right? These things have to happen at the right order. So the CPU actually has to keep track of these things. And what it ends up doing is it looks at the relationships between instructions, it orders them correctly, but as long as this write back hasn't happened, this memory access cannot be allowed to proceed. And so what actually happens is that the second instruction, the load from memory, stalls. It just waits for the previous instruction to complete, and you lose an opportunity for computation. Does this make sense? I hope so. Okay, I've seen a few people nodding, the rest are probably sleepy. It's fine. I mean, come on, it's before noon. We're not used to waking up at this time. Sorry. So if you're coming from more of an academic background, you might notice this pipeline bubbling. It basically means the same thing. I just don't really like this word. Right. all of this has been theory. Let's tie this to real life. Let's have a look at some practical ramifications. The first thing you need to know is that memory is slow. Now, you're kind of not used, most of us anyway, are not used to thinking of system memory as being slow. We're used to thinking of hard drives being slow. We're used to thinking of network being slowish, right? We're not thinking of system memory as something that is slow. But even on a very modern CPU, RAM access, like actually going to your, your memory stick installed on your motherboard and reading some stuff off it, takes about 60 nanoseconds. So what this means, and these are actual numbers for a modern Skylake-based CPU, so it's not like the latest Intel CPU, but it's modern enough. It's the sort of CPU that you're liable to run into in your data centers, your cloud providers, etc. It's a 64-bit CPU. It runs at, in this example, 4 gigahertz. So what you actually get is 60 nanosecond translate to 250 CPU cycles. What this means is that as long as you're actually waiting for something to come back to you from main memory, you have lost 250 opportunities for computation. When you put it like that, it seems terrible. Memory is dreadfully slow. It stops us from actually performing the work that we want to do on the CPU. More interestingly, if you just do the math in a very kind of naive way, the math gives you a total memory bandwidth of about 130 megabytes per second. And for any of you who've done any kind of intensive work, this number sounds ridiculous, right? 130 megabyte, that is just, that is, if I do this and I take a photo of you on my iPhone, just this very second, I have more than 130 megabytes running through my iPhone. And that's not even a server-grade CPU, right? So the number doesn't make sense, right? Obviously, something else is going on that is enabling us to actually get work done meaningfully. This, by the way, is for purely random access, right? You just read off a byte somewhere in memory. So surely we can do better, and we can. The first out of two kind of major themes in this talk we're going to be covering is the CPU cache. One kind of reasonably well understood, but sometimes a lot of people still manage to kind of ignore, is the fact that cache is not monolithic. Your CPU cache is not just a pile of memory dedicated to caching stuff. It's a hierarchy of caches. You have your level 1 cache, level 2, level 3. For a very modern Skylake i7 CPU, you would have 64K of level 1 cache running at full CPU speed, divided into 32 kilobytes for instructions and data. The latency there is very, very low. It's about 1 nanosecond access time for, once again, a pretty modern CPU. Your level 2 cache is bigger. There's 256K on Skylake specifically. And the access time is a little bit less happy. It's 3 nanoseconds. And then you have your level 3 cache at 4 megabytes. It's usually shared between CPU cores. This reminds me that I've forgotten a little bullet in the full disclosure. In this whole talk, I'm not going to be talking about multiple cores, SMP, or any of that stuff. There's enough complexity in just a single CPU core to be of interest. But obviously, having more CPU cores adds to the complexity. So this L3 cache might be shared between your CPU cores. It's fairly big. It's got 4 megabytes on a Skylake, and its access time is 11 nanoseconds. Main memory takes 62 nanoseconds to access. So you have this hierarchy of things where ideally you want the memory that is kind of most frequently accessed to be at the lowest level of the cache because that has the fastest access time. Now, another critical aspect of the CPU cache that a lot of people kind of miss is that the CPU cache doesn't know the concept of a single byte. It doesn't care. The atomic unit for a CPU cache is called a cache line. For most modern CPUs, not just x86, but certainly the kind of CPUs your code usually runs on, cache lines tend to be 64 bytes in size, and they use a least recently used eviction policy as part of that cache. What this means is that when you read a single bit off of memory. Like you have a Boolean flag somewhere that you read, right? You don't actually read off 1 byte from main memory. You read in the entire 64 bytes, and that gets populated in the cache. So why is sequential access? Like we all know, especially with hard drives, but it's true of main memory as well, that sequential access to main memory is very, very fast, and random access is not quite as fast. Why is that, right? There's no magic here. We may or may not know what's going on behind the scenes, but it's engineering, right? Someone had to design the thing. So sequential access is very, very fast because of something called cache prefetching. Now your cache controller and your CPU basically observes the stream of memory accesses, right? If you have an inner loop and it runs and it reads off memory sequentially, the CPU cache controller actually has a mechanism inside that looks at that stream of accesses and says, okay, well, I see that you've accessed byte n plus 1, n plus 2, et cetera, you must be doing sequential access. Well, if I, the CPU, can determine that my user is actually doing sequential access to memory, I don't have to wait for stuff to come back from memory. As soon as I determine that the access is sequential, I can start reading stuff off ahead of time from main memory and populate my local cache. This is called cache prefetching. And this is the thing that guarantees that when you have like a very heavily optimized inner loop, such as your jitter might generate for you, it makes sure that the memory is ready in advance so that the actual computation pipeline can proceed as fast as it can. It doesn't have to wait for anything to come back from main memory. Does that also make sense? Cool. So that is kind of an important optimization. Now we get to the ramifications, right? All of this stuff is designed to give you the illusion of a very, very, very fast CPU and very fast memory subsystem, and there's a lot of optimizations under the hood to make you not care about your pattern of memory access or the way you do your computation. But it sometimes breaks, right? If you have certain types of computation, you might not be taking advantage of these mechanisms. In fact, you might be hindering their ability to get work done. So one kind of classic example of this is image rotation. We have here what some would call a cat, and we want to rotate this image of the ostensible cat. So rotating an image is a pretty simple algorithm. You have your outer loop that counts rows, that's the Y loop. You have your inner loop that counts columns, that's your X loop. And then you read off the pixel at row Y, column X, and you write it back at row X, column Y. That is essentially it. It's a very simple algorithm. And you would have expected this to, this is pretty straightforward. You would have expected this to be efficient. But it turns out that this is really, really, really bad for caching, and it's not efficient. And the reason is this. Reads are sequential. When you read the image, the source image in, you read it sequentially. When you write it, though, that is not sequential. It's linear, but it's not sequential. You actually have to jump around in memory a lot. And if the image is of sufficient size, and any kind of modern photo, even 10 years ago, would have been way larger, like an 8 or 16 megabit sensor, right? Even that produces an image that is too big to fit in your CPU cache. So whatever you do, you have to thrash around through main memory. The CPU actually has to move around with main memory, read in stuff into the cache, then throw that away, read more stuff into the cache, and it turns out to be very inefficient. The reason is what you have are different strides. A stride is the delta in memory address between subsequent iterations of your loop. So your reads have a stride of 1 because you move from like 1 byte or 1 word of memory to the next sequentially. Your writes will have a stride that is correlated to your image size. So you have different strides at the same time, and the worst case wins. So this brings us into this category of algorithms that are called cache-friendly algorithms. In the case of an image rotation, one kind of very trivial technique you would use is a technique called blocking or tiling, which is where you take the image and instead of algorithmically, instead of actually processing your whole image, what you do is you subdivide it into smaller kind of blocks, and you work on each block separately. So if we zoom in a little bit, we have the 16 by 16 pixel block of the image of the cat, and we can actually take care of that particular block and move on to the next one. And when we've finished taking care of all of these blocks, we have finished taking care of processing the entire image. So the algorithm is actually very, very similar. The inner loops look kind of the same, except we only process a block of size, block width, over block height on every iteration of the loop. And our outer loop just makes sure that we process all of the available blocks until we're done. Right? So this is almost the same algorithm, but it turns out to be a lot more cache-friendly. Let's have a quick look at, once again, JMH benchmark results. So we have kind of our baseline naive rotation version. That takes about 43 milliseconds to rotate a 4K image of a cat, assuming that's what that was. And then you have your various block sizes. You might decide on 8 by 8 pixels, 16 by 16, 48 by 48. And you can see that they're not actually exactly the same. Right? If you take a look at just the results, you can see that there are differences. There is an optimal block size that correlates to your caching subsystem and makes the most efficient use out of that. What that is doesn't matter because every single version is roughly twice as fast as the original code. And this is actually for very naive code. There are other ways to optimize it. And the crucial point here is that while you may not necessarily be writing code that cares, that needs to take advantage of these ramifications, of these attributes of how the CPU is architected, I can flat out guarantee you that whatever libraries, whatever frameworks, whatever virtual machines your code relies on does take advantage of these aspects, does take advantage of these attributes of the CPU. If you use Netty has a lot of optimizations that have to do with effectively managing memory and effectively walking through memory so as not to just waste CPU cycles waiting for memory or waiting for the cache. Right? If you use ImageMagick for image processing, it does a lot of these tricks, right? So whether or not you actually write code that cares, the only reason why you're allowed to not care that much about the CPU architecture is because you're built on top of a layer of abstractions. You build your software on top of a layer of abstractions, and ideally each of these kind of layers of abstraction takes these things into account and gives you optimal performance. Second kind of architectural concept or architectural conundrum that you might run into with the CPU is around branching. So we've already mentioned that branching are one of the reasons for CPU pipeline stalls. But a branch is essentially the CPU asking a question, right? I have a condition that I need to evaluate, and that the results of evaluating that condition tell me which way I need to jump. Should I go left? Should I go right? Now, the CPU can't just guess at it because it doesn't know. The result of the computation depends on the system state and what the code actually does. So ideally, you would have that information ahead of time that'll let you, just completely avoid one or other of the branches and read the next instruction into memory. But you can't really wait for that information to come in because that is essentially pipeline stalling all over again. Maybe you could take an educated guess. Like as a CPU, you can look at historic trends. You can look at a particular branch and say, well, I know that this particular branch has historically resulted in my, going left or right. Think of a null check, right? You have a lot of null checks within your, emitted by the jitter within your Java code. A null check in a disciplined, well-written code usually evaluates to false, because well-written code doesn't pass nulls where nulls are not allowed. So ideally, the answer to the question, is this thing a null, is it safe to proceed, will always be yes. So if historically the answer is always the same, you can speculatively reach in and read in the next instruction if you've guessed right. And then you can proceed with your computation. Now, if you've guessed wrong, then you need, once you've realized it, you need to actually stop and flush your pipeline. This is called branch prediction. So what branch prediction does is, when it runs into an if statement, right, a conditional branch or whatnot, what it does is it speculates on that particular branch. Do I have enough historic data to make an educated guess which way the branch is going to go? Concurrently, it actually evaluates the condition, because guesswork is not enough, right? Guesswork allows you to, ahead of time, read in the next instruction and start populating the pipeline. But it might be wrong, right? A null check might eventually fail. So you actually have to evaluate the condition. But you can do these two things concurrently. It's not in parallel, it's concurrently. You can assume that you're going to need the next instruction, read it in, start decoding it, fetching it, decoding it, etc., while waiting for the results of the evaluation. Now, if you're right, then everything is fine, right? If the result of evaluating the condition ends up the same as your kind of educated guess, then it's all good. You just commit the transaction, which essentially means you don't need to do anything as a CPU. Rolling back a transaction, if you've speculated wrong, if you've fetched and decoded an instruction off of the wrong side of the branch, then you need to take that work, throw it away, and your whole pipeline has to wait for memory access for the instruction, for the correct instruction to be written and decoded, right? So it's a trade-off. If your guesses are smart enough, then everything runs faster. If your guesses suck, everything runs way slower than it would have otherwise. So that is why CPU manufacturers over the last 20 years have invested very, very heavily in kind of more and more advanced branch prediction algorithms. Circling back to where we started off. We have this code, with or without the sort. We know that the sorted version is significantly faster by an order of magnitude. Now, can you guess why? Like, obviously, the context here is branch prediction. That is the correct answer. But can you guess why the branch prediction has such a massive effect on this particular code? You don't have to answer, but I will give you about 10 seconds to try and figure it out on your own, and then I'll explain it. 10 seconds. Mm-hmm. What's that? Vectorization? No. This is naive code. Don't assume that the answer is smart. It's not. It's a very, very simple thing that's going on. Vectorization is like 2 orders of magnitude of complexity more than intended. So obviously this has to do with branch prediction, and obviously the if here is kind of the culprit. Now, let's consider what the CPU actually does for this algorithm. We have an array of bytes, just a completely random stream of bytes. Now, if we actually sort that array, we end up with all of the negative numbers on one side, all of the positives on the other side, and the 0 is somewhere in the middle. Now, the 0 actually acts as kind of a pivot point, because we, as human beings, as engineers, know for a fact that everything to the left of the 0 is, by definition, negative. So this kind of if condition always evaluates to false. On the right side, it's the exact opposite. It always evaluates to true. So what we've actually done here is we've artificially created the perfect conditions for a branch predictor, because the CPU iterates through your array, it looks at the first few elements, and it tracks what the result of evaluating the condition is. And then it says, well, okay, enough, however many times, depending on the branch prediction strategy, however many elements turned out to be less than 0, i.e. the condition evaluated to false, I can now speculatively guess with a pretty high confidence factor that it's always going to be false. And it is indeed always false until you reach this 0. And then suddenly it becomes true, right? So at that point, you have a bunch of pipeline stalls. The CPU slows down a little bit as it's processing 0 and the subsequent few elements. But the way to think about it is it actually flushes its branch prediction assumption table, and it starts looking at your if all over again. And now it looks at the 0 and says, okay, it's true. It looks at a bunch of other elements and it sees that it's true, and it's happy because, you know, it sees that its guesses about branch prediction are now once again safe. So this is the perfect setup for branch prediction to do its work. And because pipeline stalls actually, like, when your code slows down, it's usually due to pipeline stalls of one form or another. And this does show up as your CPU being busy. So if you actually end up working on low-level enough code where you care about that sort of performance, just looking at your CPU utilization is not going to be enough. You need something more. You need something to tell you that the pipeline is stalling all the time, probably due to branch prediction failure. And you can actually get at these through hardware counters if you want. But crucially, if you want to know what's going on, you need to first kind of understand the fundamentals of how CPUs are designed. And this is one of the kind of more common effects that the CPU architecture has on your particular code base. Is this reasonably understood? Awesome. And with that, I'm pretty much done. So I've covered everything I had to cover. If you have any questions, I'd be very happy to take them. If not, thank you very much for your time. I hope this was at least a little bit interesting and illustrative of the complexities of modern software engineering. Thank you very much. Any questions? I don't see anyone, so if anyone is raising their hand. Oh, okay, cool.
One question. How exactly hybrid trading works? I'm talking about situation when we have single CPU and we can handle 2 threads simultaneously, probably. I'm not sure.
So I'm not sure I'm qualified to answer that question to any meaningful degree, but as I understand it, the idea behind hyperthreading is while you only have one CPU core, if you have a pipelined CPU core, then it can actually do multiple things at once. There's multiple execution units that can do various types of computation concurrently. So the idea behind hyperthreading is they're trying to kind of force better utilization of the CPU by just parallelizing more and more. Like if you can execute 2 completely unrelated instructions simply because you have enough available execution units, then why not do that? That is kind of the idea behind hyperthreading. As to how it actually operates, sorry, I have no idea. Okay, anyone else? Awesome, thank you, have a great conference.